Okay, Scholar. So here we are in Unit 7, which will be the last unit that you guys will be responsible for on the AP exam. The last unit that we're going to learn. And really, this unit is the biggest, and there's a lot that you are not going to be responsible for on the AP exam. We are going to learn it eventually. I haven't quite figured out that schedule yet. It will either be here in a couple weeks before the AP exam or after the AP exam is over. I will get that schedule out to you as soon as I can. But for now, we need to focus on learning this last bit of information, dynamic equilibrium. This is going to be all about the idea that in a chemical reaction, let's say that we have this hypothetical reaction, we have been so far analyzing what happens when a reaction occurs from left to right. What happens when reactants combine chemically to form products? What we have not um, looked at so far, what we have been ignoring, is that most chemical reactions are actually what we refer to as reversible. So once you form products, those product molecules could collide, break their bonds, form new bonds to form the reactants again. So most chemical processes are actually reversible. They proceed in both directions at once. So if we have chemical A and chemical B in a reaction vessel in a flask or something, they start to react. We will see their concentration go down because they're forming C and D. But then C and D react to some extent. That could be a large extent or a small extent. We'll talk about that. C and D could react together to reform A and B. Um, and this process, continues to occur until the system reaches what we refer to as dynamic equilibrium. And studying what that equilibrium is, what it means, and whether the equilibrium of the mixture. So from now on, we're going to be referring to the reaction mixture, which means that we're just simply acknowledging, hey, A and B don't fully convert to C and D. My reactants do not fully convert to products. Instead, as the reaction proceeds, and even when the reaction is quote unquote finished, I have C and D in my reaction vessel, but I also have some A and B, don't I? So instead of talking about very simply reactants transforming into products, we're going to be analyzing how reactants and products end up mixed together in a certain ratio in the reaction mixture, and studying that reaction mixture and whether we have more reactants or more products in the reaction mixture and how that changes and what can affect that. That's what this unit is going to be all about. All right. Okay, so here's our first slide. This kind of is referring to what I just got done talking about. Most chemical reactions are indeed reversible, as I just stated. And here's the big idea for this unit. Any reversible reaction occurring in a closed system will reach what we refer to as dynamic equilibrium. So let's talk about both parts of that term. Super important term. It is the biggest term in this unit. The word dynamic, I hope you guys know, means changing, and equilibrium means that something is equivalent. So we have a changing equivalence somehow. Something is still changing. It's a dynamic system. There are still changes happening, and yet something is staying the same. Something is equal. So let's talk about what that means. Dynamic equilibrium is where the forward and the reverse reactions. So let me just remind you what we're looking at here. We're saying that our reactants can undergo a reaction to form the products, but the products can undergo a reversed process to form to form reactants again. It's reversible. Well, at some point, all chemical reactions in a closed system. Let's talk about what that means. A closed system means that we're not adding any extra mass. We're not adding extra reactant. We're not adding extra product. We're just letting the thing go and do what it's doing. That's what a closed system is. Any system that is closed, any chemical system that's closed, is going to reach dynamic equilibrium, where that means that the rate, so this is following right up after our kinetics unit where we were studying rates of reactions, the rate of the forward reaction begins to become equal to the rate of the reverse reaction. So those reactions are occurring at the same rate. That is the equilibrium part of dynamic equilibrium. What is the same about the forward and reverse reactions? The rate, the speed with which the reactions are occurring. Well, what's going to be true if these reactions, forward and reverse, are occurring now at the same rate? Well, it means that we're going to get no net change in the concentrations of reactants and products. This is hugely important. That is also tied up in this equilibrium idea. The system has reached a state of equilibrium. There's no longer any net change. In other words, if the forward and the reverse processes occur at the same speed, at the same rate, then A and B combine to form C and D. But C and D combine in the exact same amount of time to form A and B again. So we get no overall change anymore. There's no longer any change. The system has reached a stable point where no net change occurs. So those are the two things that equilibrium is referring to. The rates of these reactions become equal, and therefore the amounts of reactants and products become stabilized. Now listen, I'm not saying that the amounts of reactants reactants and products become equal. I'm not saying that like the concentration of A plus the concentration of B equals the concentration of C plus the concentration of D. I'm not saying that the amounts become equal. That's not what I'm saying at all. What is equal about them is the rates of those reactions. So we could say that the rate of the forward reaction has equaled the rate of the reverse reaction. That is indeed true at equilibrium. I'm not saying that the amounts become equal. But what I am saying is that whatever amounts we have of A and B and C and D, once equilibrium has been reached, once the system has reached equilibrium, and it could take a while, different systems will reach equilibrium at different speeds. Once equilibrium has been reached, because the rates are the same, then the amounts of A and B can no longer change, and the amounts of C and D can no longer change. All right. The dynamic part of that phrase, dynamic equilibrium, refers to the fact that these reactions are still actually happening. Even though if we were to take measurements, we would see no changes. Again, there's no net change in the amounts of reactants and the amounts of products. If we were to get in here and at equilibrium, the rates are equal, and we measure the concentration of A and B, we measure the concentration of C and D, we're going to see no changes in those amounts, in those concentrations. But the system is still dynamic, which means that these reactions are still actually occurring, okay? The reactions have not stopped occurring. They're just occurring at equal rates, and so we cannot see overall any change happening. There is still change happening. A and B are still reacting to form C and D. It's just that C and D react right back at the same speed to form A and B again. So that's where the dynamic comes from. You all need to make sure that you have your heads wrapped around this idea of dynamic equilibrium before you go any further. And this will become more clear once we see examples and graphs and things like that. All right? This statement down here, this will make sense a little bit later as well. What this is saying is that equilibrium states may favor forward or reverse reactions. In other words, once these rates become equal, once the rate of the forward reaction equals the rate of the reverse reaction, notice what I said earlier that does not mean that the concentrations of A and B are going to be equal to C and D. The reaction system could have favored the production of products, in which case the concentration of products will be greater than the concentration of reactants. In that case, we say that the equilibrium position lies to the right, or we say that the forward reaction was favored, because overall, once we've reached equilibrium, once the rates have become equal, we have formed more product. All right. So once again, equilibrium does not mean that the concentrations are the same. One side is going to win out. One side is going to have more stuff than the other side. If the product side is favored, if the forward reaction is favored, then we say that the products are favored over the reactants, the forward reaction is favored, or we can say the equilibrium position lies to the right of the system, right? If the equilibrium position lies to the left, the exact opposite is true. If the equilibrium position lies to the left, that means that the reactants are favored. So we have more reactants than products. There has not been a lot of motivation for the system to form products. There's not been a lot of motivation for the system to undergo forward change to make these products. So we say that the reactants are favored, the reverse reaction is favored, or we say that the equilibrium position lies to the left. We'll be talking about that more. Whether the forward or the reverse reaction is favored depends on a lot of things, but really it depends on the thermodynamics, on which process is favored. And you guys know that any process that is favored has to have a negative delta G, right? So the process that has the biggest negative delta G is going to be the process that is favored. We're not going to get into this. This is not part of the knowledge you need for the AP exam this year. We will talk about it after the AP exam or some point in the future. All right, but it all does depend on whether we form more products or whether we end up with more reactants. Does depend on the relative free energy changes that we can get from the forward and reverse reactions. Okay. All right. So big ideas here. Dynamic equilibrium. It means the rates are equal. And there's no more change. We can end up with having either more products, in which case we say the forward reaction is favored or the equilibrium lies to the right, or we could end up at equilibrium with more reactants, in which case we say the reverse reaction was favored or the equilibrium lies to the left. So make sure you study and understand all this terminology and make sure you're able to use it. Hopefully through some examples it'll make more sense. So let's proceed. Okay. All right, so these two graphs, you need to study them, you need to know them. This is overall a graphical version of what I was telling you before. All right, so let's say that our reactants here are A and B, and let's say our products are C and D. And so we know that we have reactants A and B going in a forward process to form C and D, but C and D can go in a reverse process to form A and B again, all right? So this graph here, you know, we've studied before, and this graph here should also make sense to you. Think back to the kinetics unit. As the forward reaction occurs, the amount of reactants that we have is going to drop because they're getting consumed in the forward process, all right? And as the reaction proceeds, the amount of products we have build up. But those products are going to react together to some extent. It could be a small extent or a large extent. They're going to react together to form more A and B. And so we can see, therefore, that we have two rates that we're talking about. Instead of just one rate, we have two rates. The forward rate of the reaction is occurring. And you can see that the forward rate is slowing down. That makes sense because you guys know that rates are proportional to concentration, right? Remember your rate laws. So the rate law here would be K, concentration of A to the N times concentration of B to the M, right? And so, of course, as the process proceeds to the right, as the forward reaction occurs, our reactants get consumed, the concentrations go down, therefore the rate goes down. And that's exactly what we see here. For the reverse rate, it's the exact opposite. In this example, my reverse rate would be K times the concentration of C to its own N value times the concentration of D to its own order. And we know that the concentrations in C and D are rising as time goes on. And so the reverse rate would be increasing. So the forward rate is dropping. The reverse rate is rising. That makes perfect sense based on what we know from kinematics. If rate is proportional to concentration, A and B are getting consumed, so the forward rate drops. C and D are getting produced, their concentrations increase, so the reverse rate, their rate, going back the other way, increases. And at some point, you can see right here, we reach equilibrium, where the rates are equal. That is the definition of equilibrium, all right? If we come down here and study what's happening with the actual concentrations or amounts, A and B fall, C and D rise, just like we would expect. And then we can see that once equilibrium has been established, there is no more change in the amount. The amount becomes constant. We get one constant amount of C and D products and one constant unchanging amount of A and B. So equilibrium entails both of these things, equal rates and unchanging amounts of chemical species in your system. Does it mean that the reactions are no longer occurring? No, you can see the rates are non-zero. The reactions are still occurring. It's just that because they're occurring at equal rates, for every C and D that get produced, we produce an A and B again because the rates of the forward and the reverse are equal. So that results in no net change. All right. So we could study this, and we could, just by looking at these graphs, answer the question, is the forward reaction favored or the reverse reaction favored? Well, we can see here that the forward reaction in this example is favored. So we could say that the forward reaction is favored, or we could say that equilibrium lies to the right. Why are we able to say that? Well, I can see that once equilibrium has been reached, what do I have more of? I have more products, don't I? So that is going to be my clue that this forward reaction was favored. I ended up making more products and consuming more reactants. The reverse could have been true, and we'll analyze some examples of that. But hopefully you guys are getting the hang of equilibrium. All right, so we need to talk about why equilibrium occurs. Why do systems reach an equilibrium? And this, you should be able to answer this on your own now. I've kind of already talked you through it in that graph on the previous slide. We know from the last unit that molecules react through collisions. We know that the more collisions there are, the faster the reaction, and that the fewer the collisions, the slower the reaction. And we know that the rate depends on concentration. Think about your rate law once again, right? Rate depends on concentration of reactants. And why is that true? Well, if you have more reactants, you're going to get more collisions, and then you're going to get a faster reaction. So here's the idea. You guys can read it, make sure you understand it. It's just what we talked about on the graph before. As the forward reaction proceeds, the concentration of reactants decrease while the concentration of products increase. Fewer collisions occur between the reactants, therefore the forward reaction rate drops, while the rate of the reverse reaction is speeding up because we're making more products and we get more collisions occurring, and therefore the rate of the reverse reaction increases. And eventually the forward and the reverse rate will become equal to each other. This slide is just explaining in words the graphs on the previous page, okay? All right, this is super important, so listen up, nerds. There is a value that allows us to describe what a system is like at equilibrium, and we call it the equilibrium constant K. Sometimes we refer to it as K with the little subscript EQ. I think that's redundant because we know that K is the equilibrium constant. We're going to see that there are special types of K that describe special types of equilibrium for special types of systems. We'll talk about that later. So for now, you can just write K or K sub EQ if you want to. K is built around this thing known as the law of mass action. For a system at equilibrium, so the system has already reached equilibrium. This is only true when we are at equilibrium. We'll see later that something else is true when we're not at equilibrium. When we are at equilibrium, at a given temperature, so this is temperature dependent, that's very important for you to understand. Temperature is going to change this K value. But for a given system, at equilibrium, at a given temperature, this ratio right here will always be a constant value, and that value is K. So here's what I'm saying. At given temperatures, every chemical reaction, every reversible reaction, every chemical system has its own unique K value, all right? Its own unique K value at that given temperature for that given system. So let me talk to you about this law of mass action equation. Here we have a reversible reaction. this arrow is not indicating that it's reversible. So let me draw a little reverse arrow there, where A and B are my reactants, C and D are my products. And the little a, little b, little c, and little d, very, very important. Those are stoichiometric coefficients, right? So this is just a balanced chemical equation where A, B, C, D are, little a, little b, little c, little d are just the mole ratios, the stoichiometric coefficients that you would put in your balanced chemical equation, all right? So the law of mass action, this K value at a given temperature is equal to something very simple. On the top of the ratio, we have our products, the concentration, right? That's what the brackets mean. Concentration of products raised to their stoichiometric coefficients multiplied together. Now, right away, I'm anticipating that people are going to confuse this with something else. First of all, we have differential rate laws, right? And the differential rate law looks like this for this reaction. For the forward reaction, I could write the rate law like this. Right? Two big places to not get confused and not get things mixed up here. This K value is a rate constant. That is not the same K value here. This is the equilibrium constant. This is an uppercase K. This is a big boy K that helps us understand what's happening at equilibrium. This is a lowercase K that's that goes into help us understanding the rate of a reaction. So don't get your two Ks mixed up. They are not the same. Another big place for confusion is that these exponents here, remember how they were discovered? They have to be discovered experimentally. The exponents that we're using in this equation, are they discovered experimentally? No, they're easy. They're just the stoichiometric coefficients, all right? Remember that for a rate law, you cannot use the stoichiometry of your equation to get those exponents. You can only use experimentation. There is one, so this is just a review from last unit. There is one time when you are allowed to use stoichiometric coefficients from a balanced equation as the order on the reaction, and that's when you know the rate determining step, the rate dependent step, the slow step in a mechanism, all right? So please don't get all this confused. Please try to keep it straight in your heads. Please go back and review rate laws and rate mechanisms so that you understand these exponents from last unit. Do not get this equation confused with this one. Okay, this is describing equilibrium of a reversible process. This is a rate law describing the rate of just one process. All right, I hope that everyone can understand that and can get that straight. Okay, so let's talk about this equation again. At any given temperature, any chemical system will reach equilibrium as long as it's a closed system, where closed means that we're not adding any extra A, B, C, or D. We're not adding any extra chemicals or taking any out. Any closed chemical system will always eventually reach equilibrium. When the system has reached equilibrium at a certain temperature, this ratio will always be one value that we call the K value. Every chemical reaction system has its own unique K value per temperature at a given temperature. All right, and it's always going to be equal to this ratio of the products, the concentration of the products raised to their stoichiometric coefficient, divided by the concentration of reactants raised to their stoichiometric coefficients, okay? So please keep that straight and make sure that you understand this equation. Be a good thing to memorize. I mean, it's pretty simple. Concentration of products raised to their stoichiometric coefficients in the balanced chemical equation divided by the concentration of reactants, each raised to its stoichiometric coefficient in the balanced chemical equation. All right, so I want to note something real quick. There is only one equilibrium constant for a particular system at equilibrium at a specific temperature, but we could get an infinite number of concentrations, right? In other words, if your equilibrium constant is like a 2 or something like that, there's an infinite way that we can multiply stuff here and divide by stuff to get a 2. Does that make sense? So one equilibrium constant can have multiple iterations. It can have multiple concentrations here. All right, here's another super important thing. This is probably even more important than that previous note. Solids and liquids do not get included in this expression, all right? So you only include gases and aqueous stuff. Why is that the case? Because these are concentration values. We cannot even talk about the concentration of a solid or a liquid. They have no impact. This is really, really interesting. Solids and liquids in a reaction have no impact on equilibrium. They do not impact the equilibrium at all. They can have an effect on the rate of the reaction or what happens to equilibrium. We can talk about that, but solids and liquids, pure solids and liquids, do not show up in the equilibrium expression at all because we cannot even measure or talk about the concentration. Remember, concentration is moles per liter. Or molarity, right? Moles of a gas per liter that the gas is trapped in. Moles of an aqueous solution per liter of solution. Moles of an aqueous solute per liters of aqueous solution. So we can talk about concentration of gases and aqueous stuff. We cannot talk about it for solids and liquids. So solids and liquids are not included in the law of mass action. They're not included in this equation, all right? So, for example, if A was a solid, I would not include it at all in that equation, all right? Okay, let's talk about what K means conceptually. K, the value of big boy K, is going to show you if the equilibrium system lies to the right or to the left. It shows you the tendency for a reaction to occur and the extent to which it occurs. So let's think about this. I'm going to write down here the equation for K. And of course you have to modify this. I hope you guys understand you have to modify this based on what your reaction is. We're just looking at some hypothetical chemical reaction where A and B, where A and B are reactants and C and D are products. Okay, so I want you to think about, and this just makes perfect mathematical sense. If your K value is big, if it's bigger than 1, if it's not a fraction or a decimal, then that means that we end up with more products on top, right? If this top part of the equation is bigger than the bottom part, we are going to end up with a value here where K is greater than 1. That means that the formation of products is favored. In this reversible system, we would say that the equilibrium lies to the right, or that the products are favored, that the system favors the production of the products. If your K value is really big, like 10,000, 100,000, maybe even 1,000, that means that you have so many more products at equilibrium than you do reactants that the system might as well go to completion, that the forward process happens and the reverse process does not really even happen at all. So a very large K value indicates that basically we're looking at just a one-way reaction system, because a very big K value means that we would end up with a lot of products and not a lot of reactants, okay? The exact opposite is true when our K value is less than 1. If our K value is less than 1, how are we going to get an answer that's less than 1 in this equation? How are we going to get a decimal or a fraction? Yeah, when the bottom is bigger, right? So right here, and remember, these values are the concentration at equilibrium, once equilibrium has already been established. So once equilibrium has been established, if the concentration of A and B, my reactants, are bigger, my equilibrium constant, my K value here, is going to be a small number, which means that the formation of reactants is favored, and the equilibrium, I would say, lies to the left. If my K is so tiny, like 0.00001 or something like that, if my K value is some really small decimal or really small fraction, that means I've hardly formed any products at all. And so basically, the forward reaction did not occur to any significant extent. That I've just remained, that I just have reactants remaining. I haven't made any products really. All right. So this K value then can help us understand whether the forward or the reverse process is favored. Big K value means products is favored. Really big K value means products are super favored and the reaction pretty much goes to completion. And a K value that's less than 1, a small K value, means the reactants are favored. The reverse reaction is favored. The equilibrium system lies to the left. And if your K value is really small, that means that really the forward process has not happened at all. So K can tell us about the tendency of a reaction to occur. Is the forward process favored? Is the reverse process favored? It does not tell us how quickly a system will reach equilibrium. So this is a misconception that people have. They think a big K value means that the system is going to reach equilibrium really fast. That, the bigger the K value, the more the system and the faster the system is going to form products. That is not necessarily true. So K value is more related to favorability and thus to delta G, which I talked about earlier. The K value is telling us what's favorable. Big K value means that the forward process is favorable. Small K value means that the reverse process is favorable. So K is tied to delta G. And remember, delta G doesn't tell us anything about like how quickly a reaction occurs, the speed with which reactions occur, and therefore how much time it takes for a system to reach equilibrium. That's all going to be related to kinetic factors, what we talked about last unit, okay? So hopefully you understand now conceptually what the K value means and what it does not mean. The K value is going to tell you what process is favored, forward or reverse. Because it tells you the relative amounts of products to reactants that you end up with. That's what the K value is. And it can tell you things about favorability of the forward-reverse reactions, but it can't tell you how quickly the system actually reaches equilibrium. Please, please, please remember that the K value is calculated using concentrations at equilibrium once the system has already reached equilibrium. So it's measured from a perspective of equilibrium where the system is already at equilibrium. This is just what I was getting at earlier. A very small K value means that we have mostly reactants. In fact, the products have hardly formed at all. A huge K value means that we have mostly products. The forward reaction was favored. And somewhere in between, an intermediate K value means that we end up with a significant amount of reactants and products in our equilibrium mixture. A lot of reactions are going to be like this, the ones that we're going to be interested in studying, because we're going to want to know how many reactants and products, both of which we have significant amounts, we're going to know what that reaction mixture is like, what that equilibrium mixture is like. All right, so hopefully this gives you a good visual for that last slide. This is just a quick note that we can, if we have a reaction system that's all gas, we can express K in terms of pressure, give us this value Kp. So remember that the other K value we were looking at used concentration. But because pressure is related to the concentration of a gas, we can convert concentration to pressure and construct a K value for the pressure of a gaseous system. All right, it works the exact same way. We would take the pressure of reactant C raised to its stoichiometric coefficient, product C, times the pressure of product D raised to its stoichiometric coefficient, divided by the pressure of reactant A raised to its coefficient times the pressure of reactant B raised to its coefficient. All right, so if we have pressures of gases, the equation works in the exact same way to give us a K value in terms of pressure. It's a different K value. The numbers are going to be different, but they mean the same thing. You can convert the normal K value into a pressure K value with gases by using this equation. I don't think you guys have to do this on the AP exam. So yeah, I don't quite think that you will have to. Let's go over how this equation works. If you know the K value, where that K value is measured from equilibrium concentrations, you can convert it into this pressure value by multiplying it by the gas constant R, the temperature T, and then raising it to this exponent delta N, where that's the total moles of gaseous products minus the total moles of gaseous reactants. So in this case, in the balance equation. So if my equation here is this, then that delta N value, that shows up in this equation, where again, this equation is helping us convert equilibrium concentration constant to equilibrium pressure constant. That delta N would be equal to the total number of moles of gaseous products in the balance equation, which would be C plus D, minus the total number of moles of gaseous reactants, A plus B. That's how you would get that delta N. I don't think you guys need to know that, so I'm not going to worry about that too much. You do need to know that, we can use pressures here for for reactions that have gases to get a K value that works the exact same way, just from the perspective of pressure. All right. Reminder that K is dependent upon temperature, so you're going to have a unique K value for a reaction system at a unique temperature. If the temperature changes, then our K value is going to change. The equilibrium mixture will change. The ratio will. We'll talk about that later. And let's say that we so the K value that we have, as it has been written, has products on the top. And this is us taking a specific perspective. This is us taking the perspective of A and B being like reactants in our system, and C and D being like products. But if a reaction is truly reversible, if it's truly reversible, then couldn't we treat these guys as reactants? We sure could. So we could flip this whole thing and treat them as reactants. And that would be a perfectly acceptable perspective to take. If we did that, if we wanted to treat the products like reactants and flip it, then what does that do to our K value? It just flips it, right? It just turns it over, because now A and B are like our products. They would come to the top, and C and D are like our reactants. They would go to the bottom. That's what this is getting at, that if we're flipping our perspective such that we're considering the products now to be reactants, then the K value of this is going to be a new K value that we could call K prime maybe, and it's going to be related to the old K value by just flipping it, by taking the inverse, just like that. That's what this equation is getting at. So again, we have to take a specific perspective when we're defining our K value, and we can flip that perspective and thus flip our K value. Okay guys, so we need to start looking at some examples here so you can apply your knowledge that you've gained about equilibrium. So this example is about the Haber process. This is basically the industrial process that produces ammonia. So we want an equation. It takes gaseous nitrogen and hydrogen to produce ammonia. So we know that nitrogen and hydrogen are diatomic, just like this. Again, equilibrium is all about reversible reactions. These are all gases. I want to remind myself about that. That matters in equilibrium because remember, as we will remind ourselves later, the equilibrium expression, the equilibrium constant, does not include solids or liquids. And of course, we want to balance this. We get a 2 right here, we get a 3 right here, and it's balanced. So we see that this takes high temperatures and pressures to actually shift this equilibrium to the right and make a lot of ammonia. And it's saying at this high temperature, we perform the reaction, we let it reach equilibrium. So these are actual equilibrium concentrations. And so you can see the equilibrium concentrations here. We want to use those in part A to calculate the equilibrium constant for the process. So remember, the equilibrium constant, big daddy K, sometimes called KEQ, is a ratio of products, the concentration of products raised to their stoichiometric coefficients, So NH3 raised to the power of 2, you multiply that across for each product. I only have one product here, so just NH3 raised to the second power divided by the concentration of N2 raised to its stoichiometric coefficient of 1 times the concentration of H2 raised to its stoichiometric coefficient of 3, just like that. So this is the overall equilibrium expression that would give me the equilibrium constant K for this reaction. And now all I have to do is plug and chug. Please remember that in this equation, these must be the concentrations at equilibrium when the system has reached equilibrium. And these concentrations that were given to me are indeed for when the system has reached equilibrium. So my concentration of NH3 is 3.1 times 10 to the negative second. And I got to square that, divided by the concentration of N2 at equilibrium, raised to the first power, and then the concentration of hydrogen. And I need to raise that to the third power because hydrogen's stoichiometric coefficient was at 3. And that's it, my dudes. All we got to do is type that bad boy into our calculator. So when we do that, we get a pretty big number. Looks like 3.795 times 10 to the fourth. And I do need to think about sig figs. Looks like each of my equilibrium concentrations have 2 sig figs. So I need to round this guy to 2 sig figs. 3.8 times 10 to the fourth. Remember, that's a good thing about scientific notation is that it retains all the sig figs. And something else to think about is that K is always written without units. We don't really care about the units of it. It doesn't really have units. It's unitless. It just expresses a ratio. So now we want to say what this means. I notice this equilibrium constant is very big. That's a big number. So what does that tell me about this process at 127 degrees Celsius? That tells me that the forward reaction is favored. In other words, you can see that generally speaking, I have much more product than I have reactants at this temperature. That is what this K value helps you to think about. This is a very high number. Large K values, large equilibrium constants, tell you that the equilibrium position lies to the right. In other words, the products are favored. We have a lot of products here on the top of our ratio, giving us a big number. That's what a big K value means. All right, part B is calculate the K value for the reverse reaction. So the reverse reaction would just be looking from ammonia's perspective now. So I'm going to take my equation from earlier and just flip it. And I am looking from the perspective of ammonia. And so now it's like ammonia is my reactant, and these are my products. So I can write a new equilibrium expression for this. I might want to call it K prime to say that it is a new version of this. And you can see that now these guys are my products. They were on the bottom before. They're going to be on the top now. And ultimately, we're going to see that this new K expression for the reverse reaction looks exactly like the equation I had for the other reaction, looking at it with N and H as my reactants. It looks exactly the same, except it's just flipped. So it is going to be equal then to 1 over this value, 1 over my regular K value, the reciprocal of my regular KEQ. Hopefully you can see that I've just flipped the equation. And so the answer, I don't need to really calculate again. It's going to be the reciprocal of this, 1 over 3.8 times 10 to the fourth. And that's going to get me a very small value now. That gets me about 2.6 times 10 to the negative fifth. It makes really good sense that we would get a tiny answer because we know that this process favors ammonia. That is what the large K value kind of helped us think through here. The forward process is more favored. That means that at equilibrium, we end up with more ammonia than we do our reactants. And so if we're shifting our perspective to think about the reverse process, of course, the reverse process is not going to happen to a significant extent. That's why the reverse process has such a tiny K value, all right? Okay, so part C, now I want to calculate the value of the equilibrium constant for this reaction. Let me draw my reverse yield arrows. Okay, so you can see that this is the exact same reaction process now. It is just that I have taken my stoichiometric coefficients and I've divided them all by 2. In other words, I'm kind of taking the perspective of forming 1 mole of ammonia. So just to remind you, the balanced equation that we had last time was N2 plus 3H2 yielded 2 ammonia, 2 NH3. And now I've just divided all these coefficients by 2 to force my perspective to be the formation of 1 mole of ammonia. Does that make sense? So we haven't talked about this, but all I've done is I've just modified those coefficients, those stoichiometric coefficients, by dividing them all by 2. What effect do you think that is going to have on our K value? Well, let's see. My new equilibrium expression, we'll call this one a double prime or something. This is like a related series of questions. So I'm just trying to remind myself that, hey, this K value I'm looking at is related to the first one I calculated. So once again, it's just going to be the product raised to its stoichiometric coefficient, but this time that's a 1, right? Divided by the reactants raised to their stoichiometric coefficients. I'm raising this one to 1/2 now, the 1/2 power. And H2 I'm going to raise to the 3/2 power. Now, for those of you who are really confident in your math skills, you might be able to answer this question. How is this expression here related to this expression here? Well, you can see that I've divided these by 2. It was into 3H2, 2NH3. I divided everything by 2, which means that my exponents get divided by 2. The 2 becomes a 1. The 1 becomes a 1/2. The 3 becomes a 3/2. So I have taken every single exponent here and divided it by 2. Mathematically speaking, then, it's exactly like saying this, that my new K value, my K double prime, for this reaction, where I'm taking the perspective of forming only 1 mole of ammonia, so I've divided all my coefficients by 2, that is just going to be equal to the old K, the original K that I got in part A of this question, raised to the power by which I have modified the coefficients. In other words, what have I done to my coefficients? I divided them all by 2. I did have a 1, a 3, and a 2. Now I have a 1/2, 3/2, and 1. I divide each of them by 2, right? So I multiplied them by 1/2. So I'm going to raise my KEQ now to the 1/2 power. It's the exact same. Because that's what I'm doing. That's how I'm shifting, modifying, adjusting this old KEQ value now in my new perspective where I only form 1 mole of ammonia. I have 1, 1/2, 3/2. That is multiplying each of these exponents by 1/2, which if you know anything about exponents, it's like raising the whole thing to the 1/2 power. And that's as simple as it gets. This was not discussed in the notes, but you do need to know this, that the k value for a normal balanced equation can be modified to get a new k value when you have divided or multiplied the coefficients. Here I've multiplied them by 1/2, divided them by 2. So my new k value will be my old k value raised to the 1/2 power. If I had multiplied them by 2, for example, if I had wanted to know about the formation of 4 moles of ammonia, so I multiplied everything by 2, 2 N2 plus 6H2 are in a reversible reaction with 4 NH3. That's just me taking the 1, the 3, and the 2 that I had previously and multiplying them all by 2. Then for this process, my new K for this would be equal to my original K. And how have I modified the coefficients? I've multiplied them all by 2. So I'm going to raise that K by 2. Here I've multiplied them all by 1/2. So I'm raising the original K to the 1/2 power. Hopefully that makes sense. Whatever factor by which you modify the coefficients in a new expression, that is going to be how you're going to modify the exponents in your K expression. Therefore, you raise the original K expression to that power. I multiplied all these by 1/2. I raised my old K value to the 1/2 power to get my new K value for this new perspective. I multiplied all these coefficients by 2. I'm going to raise my original K value to a power of 2 to get my new K value for this shifted perspective. Anyway, I'm just going to take, therefore, 3.8 times 10 to the 4th. That was my original K value. And I'm going to raise it to the 1/2 power. Raising something to the 1/2 power is like taking the square root. Hopefully you guys know that. And I end up getting 194.94 for this. Not as big, which is what I would expect. I start with less reactant here. To encourage you guys to pause the video, read it, and try it your own dang selves. Basically, we are looking at this chemical reaction between gaseous sulfur dioxide, that's SO2, it is a gas, and gaseous oxygen, that's diatomic O2, in a reversible reaction to form gaseous sulfur trioxide, SO3. Let's balance this. I have 4 oxygens on the right, or on the left rather. So it looks like the only way I'm going to get those equal to each other is to get 6 oxygens just like that. So 2 sulfurs, 1, 2, 3, 4, 5, 6 oxygens, 6 oxygens. There we go. Okay, so we have 2 experiments. We're doing both experiments at 600 degrees Celsius. This is not something I mentioned in the last example, but the temperature does matter because the K value will be different at different temperatures. I'm doing both of these experiments at 600 degrees Celsius, and I'm performing the same chemical reaction. So I should expect that the K values in experiment 1 and experiment 2 will be equal to each other. That's what I'm trying to show, is that K1 equals K2. Show that the equilibrium constant is the same in both experiments. Well, we can see that we start with some initial concentrations. We have a mixture of reactants and products that we begin with in our reaction vessel. We let the system react, we let it do its thing, forward reaction, reverse reaction will occur, and then the system reaches equilibrium. And we want to show that the equilibrium constant for both experiments 1 and experiments 2 are the same. You can see that in experiment 1, the equilibrium concentrations that we reach of these substances are different than those in experiment 2. That doesn't matter. We should still get the same ratio, the same K value for them. This is what I mentioned in the notes, that for a single K value, for a single equilibrium constant at one temperature, there are an infinite number of combinations that you can get in your ratio to achieve that K value. And that's what this question is helping you think through. Okay, so go ahead and give it a try. Prove to me that the K in experiment 1 does indeed equal the K in experiment 2. Okay, so here's our answers, and yeah, they're pretty close. Now, they're not exactly precisely close. Why do you think that is? This always happens in chemistry, where we're a little bit off from what we would expect. That's just because we're limited in our measurements. We're only measuring out to 3 sig figs for each of these, which is not a whole lot of sig figs. So we still should be pretty confident in our results that these are basically the same. So 2 different equilibria have been reached in these 2 different experiments, but the K values, as long as the temperature is the same for that reaction, should be the same, or at least pretty dang close to it. Now, something interesting that I want to mention. Well, first of all, hopefully you didn't use the initial concentrations to solve this. The K value states what is true of the system at equilibrium. At equilibrium, these do not change, right? That's the whole point of equilibrium, is that the system has reached this stability where the forward and reverse reactions do indeed occur still. Remember, it's a dynamic equilibrium, but they occur at equal rates. And so we get no net change in amount of crap, in the amount of reactants and the amount of products. And that's what equilibrium is. So hopefully you use the equilibrium concentrations to do your calculation. Equilibrium concentration of my product raised to its stoichiometric coefficient of 2 divided by equilibrium concentration of my reactants raised to their stoichiometric coefficients of 2 and then 1. All right. So hopefully that was not too difficult for you to set up, and hopefully you did not use the initial concentrations. We don't want the initial concentrations. This is what we start with. We let the system do its thing. It's going to react forward, back, forward, back, forward, back, forward reaction, reverse reaction, and then reach this equilibrium state. All right. One thing I want to point out that's interesting is that here in experiment 2, we started with 0 oxygen. We didn't start with any oxygen. So how did the reaction proceed? Well, the reverse reaction must have been happening pretty quickly at the beginning there, right? That's how we got some oxygen to react, to let the forward reaction happen again. So this is interesting that just by mixing one of the reactants and the product must be decomposing, the reverse reaction must be happening to give us some oxygen that is then able to react and go back the other way, back and forth, back and forth, back and forth, until equilibrium once again is indeed reached at this relatively stable constant ratio according to our equilibrium equation. Hopefully you all are getting the hang of this. Let's do one more example. This is really quick and simple. Write an equilibrium constant expression for solid phosphorus pentachloride. So phosphorus pentachloride, and it's a solid, decomposing to form liquid phosphorus trichloride and chlorine gas, just like this. Looks like, trichloride. Looks like this is already balanced, right? So my equilibrium expression is going to be the products, the concentrations of the products raised to their stoichiometric coefficients of 1 and 1, divided by the concentration of my reactant raised to its stoichiometric coefficient, which is 1. Is this the correct answer? No, it's not. Why not? Because once again, y'all, solids and liquids do not show up in the equilibrium expression. This is really interesting, but the amount of solid and liquid that we have has no bearing at all on equilibrium. Equilibrium is measured in concentrations, or for gases we could even measure in pressures, right? You can't measure the concentration or the pressure of a solid or liquid. the amounts of solid and liquid have no bearing on what happens with equilibrium. So this is incorrect. The equilibrium constant K is just purely going to be my gaseous product raised to its stoichiometric coefficient of 1. That's it. So this is really interesting. This tells me that for this reaction at a given temperature, the concentration of chlorine gas that I get will always be one constant value. We get some really interesting, surprising results when we have heterogeneous reaction systems like this. You guys know that heterogeneous means different. They're in different phases. The surprising result is that the equilibrium does not depend at all on what the solid and liquid are doing, but just on what the gas does. Only gases or aqueous solutions end up in your equilibrium expression, so please don't forget that. All right.